Hey everybody, I want to pick up where we left off in class today. So we left off with you guys trying to visualize movement of water into and out of an onion cell. And we had some trouble taking a look at that onion cell, but nonetheless, I think you guys got the right idea on what to do. All right, so let me get my pen here. So we're going to start talking about some movement through the cell, but we're not going to start with water. Let's just say that a certain type of molecule needs to get through the cell membrane, okay? So imagine this to be like oxygen, for example, okay? Let's just pretend this is oxygen, okay? Oxygen can freely pass through the cell membrane. It's got a relatively even charge on it, so it's going to be able to go through. And so remember, things that can freely pass have a couple properties. They have to be really small and non-polar, because remember, this is a pretty thick lipid layer. It doesn't look that thick compared to the phosphates, but it really is in real life. So if it's going to get through this big thick lipid layer, it's got to also be non-polar, because it'll get repelled if not. All right, so notice that there's a high concentration over on this side and a low concentration over this side. So although there's going to be movement back and forth, because they can, again, freely go back and forth, but you got to imagine these things are just kind of like randomly moving around everywhere. So over time, everything's going to even out. There's going to be equal number of brown balls on either side. All right, but if we look at the net movement, more molecules will be going this way than these going this way. The chances of these coming over here are very low. All right, so anytime you have diffusion, there's going to be a net movement from high concentration to low concentration. Okay, so if I didn't provide the arrow for you and I said that these molecules were going to diffuse, you would draw in the arrow yourself. So you would locate the area of high concentration, and as long as those things are small and nonpolar, there will be a net movement this way. All right, and so that's an example of passive transport. That means that the cell does not use ATP for this. Oops. Okay, so this happens just due to the molecules having a bit of heat on them and moving around and bouncing into each other, and it's just random molecular movement, okay? Now, once in a while, though, you have molecules that are fairly small still, but they're polar, okay? So think of this like maybe these are polar amino acids that need to get into the cell. Okay, so let's say this is like in your intestine. We have to absorb amino acids from our food. Well, sometimes they're polar. So facilitated diffusion is going to help that, okay? And so this is a transport protein, and since it goes all the way through, we say it's an integral transport protein. Oops, protein. Okay, there we go. So this protein, especially because it has basically R groups on the outside that are nonpolar, which is why it kind of sticks in here. And then on the inside, there's this tunnel, and those would contain, this would contain our polar amino acid R groups, and that would help to, because polar and polar like to mix, so that would help this polar substance come through. Okay, so let's write down, this is going to be a polar substance. All right, and again, same thing here. The cell doesn't need ATP, it just needs a transport protein. So the same rules apply. We're going to go from high to low concentration again here. Okay. All right. So this shows you 3 different cells, and this time we're only looking at water moving through the cell, okay? So this right here is what we call a solute, okay? And any problem I give you, I would tell you this is a solute. And generally speaking, solutes are anything that dissolves in water, right? Oops, not letting me write. Okay, so, and as far as solutes go with an osmosis problem like this, you can assume that the solute is unable to get through the cell membrane, okay? So if something dissolves in water and it's a solute, chances are it's not going to be able to get through the cell membrane. It's too polar, you know, it's going to get repelled by the lipids. All right, So take a look. Let's start over here. In this situation, there's equal number of solutes on the outside as on the inside. Okay, so you see there's two arrows coming in, so water is going to be able to get in. Water is also going to be able to get out, so same number of arrows. So this cell is going to stay the same size, okay? So this is what we call an isotonic solution. That means there's the same number of solutes inside and outside the cell. So water is going to be able to come in and out at about the same rate, okay? So the cell stays the normal size. Okay, let's look here though. In this case, you see there's only 5 solutes on the inside of the cell and many more on the outside. So this is what we call a hypertonic solution. Okay. So you can't use these terms on their own. These are always relative to somewhere else. So you can either say the solution is hypertonic. You could also say that the cell is hypotonic, okay? So it's always what it is in relation to what you're comparing it to. So the solution is hypertonic to the cell. The cell is hypotonic to the solution. Either statement works. Okay, now here's what happens when you have a case where there's uneven amounts of solute. I want you guys to write this down and always remember it. Water follows solutes. Okay, if you remember that, you can solve any osmosis problem. Okay, so water likes solutes. Water is going to go where the most solutes are. So find where the solutes are, and they happen to be on the outside of the cell. And you'll see there's more arrows pointing out. 1, 2, 3, 4, okay? Lots of water exiting, not as much coming in. Because what's going to end up happening is this water is going to come out and it's going to get stuck to these solutes. And once they're stuck to the solutes, they're not going to be able to go back into the cell. So the water is going to get stuck out here, and what's going to end up happening is the cell is going to shrivel up, okay? So, shriveled cell. Okay, so that's going to be what happens there. Now here on this side, now we have a hypotonic solution. So in this case, the cell has more solutes than the outside, so there's going to be more arrows coming in. There's still water leaving, but not quite as much. And this water that's coming in is getting stuck there because it wants to mingle with these solutes. And so what's going to happen is the cell is going to grow. And eventually, if this is an animal cell, there's no cell wall to protect it. So it's going to burst, okay? So let's show this bursting, okay? And anytime that happens, anytime you put a cell in fresh water, lysis occurs. So lysis is the bursting of a cell, all right? So no cell wall to protect it. Okay, so that's why anytime, we can't drink too much water because then our cells will lyse. Okay, so there is a case where if you can drink too much water. Nobody probably does that without, maybe like marathon runners and things like that run the risk of it, but no normal person does. But anyhow, you have to keep a certain amount of solutes around your cells. So you have to have a little bit of salt always in your blood. All right, just to keep the osmotic balance, okay? So this whole process is called osmosis, okay? So osmosis is the passive transport of water. All right, now let's take a look and compare to a plant cell here, okay? So again, with the hypertonic solution, you have shriveling here, you have lysis here, okay? Now for a plant cell, on the other hand, this is going to be the normal state, and we call this turgid, okay? So for plant cells, for a plant cell, they always want to be in a hypotonic solution. I mean, fresh rainwater is great for plants. We don't give plants salt water or sugar water. We give them pure water, and basically that helps keep their shape. The isotonic solution, that's okay. I mean, that would mean that there's some solutes on the inside and there's some on the outside. This is what we would call a plant if this happened, flaccid. So if you gave a little bit of a saltwater solution or sugar water solution to a plant, it's probably going to be a little bit limp. So not a great situation for plants, okay? Now, if you give them a super hypertonic solution, remember that's going to be like a really sugary or salty solution. That's not a good situation because water is going to leave and we're going to see something called plasmolysis. Okay, and at this point, a plant cell would die because of this. So that's basically when the cell membrane pulls so far away from the cell wall and it really just kind of collapses on itself. That's plasmolysis. Okay, we'll pick up here next class. Thanks, guys.